Dear professors and participants, good afternoon. I'm Guo-Cheng from Nanjing University of Finance and Economics. It's a great honor to have this opportunity to communicate with you. The title of my presentation today is Fractional Chaotic Maps with q-deformation. First, we introduce some definitions and fractional calculus on timescale. The NA denotes the isolated timescale. The NA is equal to A plus 1, A plus 2, and the A is a real number. The difference operator delta is defined as delta Fn is equal to Fn plus 1 minus Fn. For discrete fractional calculus, fractional sum, we can see in reference 1 that U is a mapping NA to R and nu is greater than 0 be given. Then the fractional sum of new order is defined by the equation 3, where A is the starting point, sigma s is equal to s plus 1, and t to the power of nu is the following function defined as t to the power of nu is equal to gamma t plus 1 divided by gamma t plus 1 minus nu. For fractional capital difference, for nu is greater than 0 and nu is a fraction, and ut defined on NA, the capital like delta difference is defined by the equation 5. For nu is greater than 0 and less than 1 or equal to 1, then the aim is equal to 1. And phi t defined on NA, the left capital like delta difference is defined as follows, where t is equal to a plus n minus 1. So the fractional difference provides us a new powerful tool to characterize the dynamics of discrete complex systems more deeply. First, we review some chaotic maps and q-deformed methods. Ham first developed the predictor or corrector formula for fractional differential equations. Then Ni and Peng applied the formula and investigated the fractional differential equations numerically. They report the cause does exist in the fractional chain systems. Furthermore, one obtained the chaotic solution of the fractional delayed logical equation and proposed the equation scheme. The experimental results show that the knob image result possesses high security. To be specific, we can start with this classical logical map. The un plus 1 is equal to mu times un times 1 minus un, or the form of difference, the delta un is equal to k times un times 1 minus un, where u0 is equal to c. The mu, k, and c are constant, where mu is a constant and un denotes the value of u after n iterations. Equation 6 arises, for example, in the case of population growth. As is known to all, for the famous logical map, it is popularized by May in 1976. The system exhibits chaotic behaviors for most values of the growth coefficient mu between 3.7 and 4. Then it is significant that Professor Wu's team proposed a discrete fractional logical map 8 as follows. They get the fractional logical map in fractional sum. Compared with the classical logical map, the fractional one has a discrete kernel function. That is, UN depend on the past information U0, U1 until UN-1. As a result, the memory effects of the discrete map means that the present state of the evolution depends on all past states. We can see for A is equal to 0 and nu is equal to 1, the discrete logic map 8 and line can be reduced to the classical one. This idea is very valuable. On the other hand, q-deformation of many classical lie groups have attracted much attention. After that, many physicists and mathematicians have proposed many q-deformation methods involving numbers, series, functions, exponents, and so on. Generally, there is no unique q-deformation method for a function or numbers. Recently, Nanjing and Sinha have introduced a scheme for the q-deformation of nonlinear maps. Specifically, they only deformed the variable x on the right side of the logic map equation. Here, they choose the deformation of x. The x is equal to x divided by 1 plus epsilon times 1 minus x. And x belongs the interval 0, 1. Another q-deformation method logic was proposed by biology as follows. We can see that the q-deformation method is applied to the both sides of the equation, where x is equal to 1 minus q to the power of x divided by 1 minus q. The q is real and x is in the interval 0, 1. Of course, here we only show you two classical q-deformation methods. Therefore, inspired by the fractional chaotic maps and the application of q-deformed method in difference equation, we consider to combine them to generate a new chaotic map. Chaotic behaviors are discussed in both 1 and 2-dimensional cases, respectively. In this study, we propose the q-deformed method is applied to fractional logical map. That is, we also deform the variable x on the both sides of the fractional equation at the same time, where x is equal to 1 minus q to the power of x divided by 1 minus q. The parameter q is a real number, and x belongs to the interval 0, 1. Let q to the power of xn is equal to xn. The equation 12 can be written as the equation 13. At this point, we get a kind of deformed fractional logic map, the equation 13. Laterally, we can extend this method to multi-dimensional fractional chaotic maps. Without loss of the generality, we can apply the q-deformation method to the following two-dimensional fractional Helm maps. That is, we deform the variable x and y on the both sides of the equation at the same time, and then we get the following equation. Where xn is equal to q to the power of xn, and the k nu nj is a kernel function. For dynamic behaviors analysis, we first obtain the bifurcation diagram of the deformed logical map. Using the numerical formula 13, set the step size of mu as 0.005, and the bifurcation diagram are plotted in Figure 1. We can see that with the change of the parameter mu, the deformed map experiences stable bifurcation and chaotic states. Then, for the deformed hollow map, we get the chaotic attractors. In this image, we give two kinds of the chaotic attractor to compare the effect of deformation. The blue part is a fractional hollow map without q-deformation. The red part is a fractional hollow map with q-deformation, and q is equal to 0.5. We can see that the chaotic attractor's bending effect is obvious after introducing the parameter q. Next, we discuss the local stability of the deformed fractional chaotic maps. In order to simplify, we only studied the two-dimensional hollow map. By inverse operator, we obtain the difference equation. At the equilibrium point, we derive the corresponding linear fractional difference equation 17. System 17 can also be rewritten in vector form as the equation 18, where y is a vector and A is a coefficient matrix. Indirectly, so we will study the stability of linear difference equation. As we know, Ambu-Series and Cermak have done meaningful research on the asymptotic stability of linear systems. We refer to the following theorem. If lambda belongs to the set S nu for all the eigenvalues lambda of A, then system is asymptotically stable. Therefore, we obtain the stability condition according to the above theorem. We must point out this theorem is only a sufficient stability condition. Therefore, people can get many such theorems. In order to satisfy the above the theorem 1, we set alpha is equal to 0.1, beta is equal to 0.05, and q is equal to 0.5. Then we get the stable solution as shown in this picture below. Okay, that's all I'm going to talk about today. In this study, we use a q-deformation method in fractional chaotic maps due to the generalized kernel function, and the new chaotic maps with q parameter hold the memory effect and exhibit the chaotic motion. Furthermore, the stability of the two-dimensional case has been investigated and verified by computer numerical simulation. Since there are many other q-deformation methods, for example, the q-fractional calculus on timescale, we'll compare the results in the future. Okay, thank you.